Okay, so we are in a one-dimensional universe, and we want to think about the relationship between localizability and normalizability. So let's say we have a wave function at t equals 0, which is some, say, real constant. C is greater than 0. We don't know what C is, but it's just some, a positive constant. Let's normalize it. Let's see what kind of constraints we get. Well, first of all, maybe we can plot this. So psi of x and 0 to get some insight. Psi of x and 0. So C is some positive constant. Here is C. And here is the value of psi of x at t equals 0. Right, it's just a horizontal line. This is x. And so the modulus squared of this represents the probability density, but the probability density clearly it's just c squared. It's the same everywhere. So this particle is clearly not localizable. So we can say that just by looking at the graph, not localizable. What does that mean for normalization or normalizability? Well, let's see what we get mathematically. So we want to do psi modulus squared in dx. This should equal to 1 if we go from minus infinity to plus infinity. Right, the particle is 100% certain to be found somewhere in the universe in which it lives. But what do we get here? So first of all, this should be true for all times, or all t. So at t equals 0, that's perfectly fine to evaluate it at that time. And we get c squared integral in dx from minus to plus infinity. And that just gives us c squared times x. And we have to evaluate x from minus to plus infinity. And that gives us c squared times, well, let's just write it out, plus infinity minus a minus infinity. So that's just a plus infinity. So that's just infinity. So c squared times infinity. And this needs to be equal to 1. The only way that's possible if c goes to 0. So that means that the particle has a 0 chance, essentially, of being found at any one specific location. So we can say that it's not normalizable. And these things go hand in hand, right? If it's not, the particle is not localizable, it means that it's also not normalizable.